Today we're going to talk about exponential functions, both growth and decay. An exponential function is a function in which there's a variable in the exponent. In the image below, the b represents the base, and the x is the variable in the exponent. Remember, with all our other functions, we've had a parent function. The parent function for the exponential equation is y equals 2 to the x power. This is because the most common growth is for something to double for each unit of time. The graph of the parent function is shown below. On the left is a table showing all of the values, and on the right is the graph with all of those points plotted and the dots connected. A function is considered a growth function if b is larger than 1. So if b is larger than 1, then the population is growing and it's called a growth function. If b is a fraction between 0 and 1, or a decimal between 0 and 1, then the function is called decay function, which decreases.
Our first example asks whether or not this function shows growth or decay. So we have to look at the base, which is right here, and see if it's greater than or less than 1. Since 3/4 is less than 1, this is decay. Now we need to graph it. So we're going to make a table with x and f of x and plug in some numbers. We can pick whatever we want for x. We can go ahead and start with, let's do some even numbers, 0, 2, 4, 6. Okay, and we're going to go ahead and plug those in. 3/4 to the 0 power is 1 times 10 is 10. And if we continue to plug these in, let's put this in here so you can see the whole thing. We get 10 times 3/4 to the 0 is 10. 10 times 3/4 squared is going to give you a 5.6. 10 times 3/4 to the 4th will give you 3.2. And 10 times 3/4 to the 6th will give you a 1.8. So now we have our x and y's, and we can go ahead and graph this. So our points are going to be 0, 10, 2, 5.6, 4, 3.2, and 6, 1.8. And we can go ahead and graph these. Go ahead and graph it on a piece of paper and then check your graph with the next slide. For this one, we have g of x equal to 100 times 1.05 to the x power. The first question asks us if it's growth or decay. Since this is our base, 1.05 is greater than 1, therefore this is going to be a growth problem. Now we can go ahead and set up a table with x and f of x. And we'll pick some even numbers again, 0, 2, 4, 6, and 8. If we plug in 0, we'll get f of x equal to 100. 100 times 1.05 to the 0 is 100. For the second one, we have 100 times 1.05 squared. 100 times 1.05 to the 4th. 100 times 1.05 to the 6th, and 100 times 1.05 to the 8th. I'm going to let you continue to plug those into your calculator and see what you get for each of your points. Then go ahead and graph those and double check your answer with the next slide. Our last example of this type, we have 5 times 1.2 to the x. We want to see if it's growth or decay, so we look at our base, 1.2. Since it's greater than 1, this is going to be a growth problem. And then we're going to go ahead and graph it, so we make a table, x and f of x. Take some points. And now we're going to go ahead and plug those x's in to find out. We get 5 times 1.2 to the 0. 5 times 1.2 squared. 5 times 1.2 to the 4th. 5 times 1.2 to the 6th, and 5 times 1.2 to the 8th. And I'll go ahead and go through some of these for you. The first one is going to be 5. Under 4, you're going to get 10.4. And for this one, you will get 21.5. So go ahead and plug in the last two for 2 and 6. See what you get, see what your points are, and then go ahead and double check your answer with the graph on the next page. For our first word problem, we have Clara investing $5,000 in an account that pays 6.25% interest per year. What will her investment be worth after 10 years? Our equation for A of t is equal to A, which was the initial amount, times 1 plus or minus the rate, to the t, which is time. So we have our initial amount is 5,000, so that goes in for A. Then we have our rate, and we need to change our rate to a decimal. So our rate is going to be 0.0625. And I get that from moving the decimal point over 2 spaces to get 0.0625. So I do 1 plus 0.0625 because they're earning the interest every year. So it's a growth problem. So now we have A of t equals 5,000 times 1.0625 to the t. Now it says we want to know how much after 10 years. So our time is 10. So A of 10 is 5,000 times 1.0625 to the 10th power. If we multiply that all out, we get that after 10 years, her account will be worth $9,167 and 68 cents. And don't forget your dollar sign. Since it's a word problem, we want to make sure we have our units. So after 10 years, starting with $5,000, she has a total of $9,167.68. In 1981, the Australian humpback whale population was 350, and it increased at a rate of 40% every year since then. We want to write a function to predict the population. So we take our A of t equal to A times 1 plus or minus r to the t, and we're going to go ahead and use that equation to find out what the population would be. So our A is our initial population. So A is 350. Our R is the rate remember we have to change it to a decimal, so we move the decimal point over 2 spaces and get the rate is equal to 0.40. Now we can plug these in to get our equation. We have A of t is equal to A, which is 350, times 1 plus or minus r. So 1, in this case, it's going to be plus because we're increasing at the rate. So 1 plus 0.40 to the t. Simplifying, we get A times t, or A of t, equals 350 times 1.4 to the t. And that's our function to predict the population of the Australian humpback whales at any time t. A city population which was initially 15,500 people has been dropping 3% a year. Write an exponential function and find the population after 6 years. So we need to find our A and our R. Our A is the initial population, which was 15,500. So A equals 15,500. And then our rate is 3% per year, so our rate is 0.03. Remember, we have to move our decimal point 2 spaces. So now we can write our function. A of t is equal to 15,500 times 1 minus 0.03, because it's dropping 3% a year, and that's to the t. Now we can simplify. We get A of t equals 15,500 times 0.97 to the t. And I just get that by subtracting 1 minus 0.03. Now, this is our function, and we want to know after 6 years, so t equal to 6, what is our population? So we plug in 6 for t. So we get 15,500 times 0.97 to the 6th power. And when we simplify that, we get A of 6 is 12,911 people. So the population has gone from 15,500 to 12,911. It's dropped almost 2,500 people.